Thank you so much. Thank you so much for having me here today. Yeah, so my name's Chris, and I'm a postdoc at Caltech right now, but I'm actually starting a faculty position next month at the University of Southern California. And most of my work focuses on how we can use astronomy and astronomical observations to try to learn things about gravitational waves and about dark matter. So today I'm going to talk about these two papers that we had published this year and a few years ago, along with collaborators at Caltech and JPL, especially Ali Wang, who is a graduate student who did an awesome job on both of these papers. So I'm sure you have all seen these sorts of pictures before that show, what the gravitational wave spectrum looks like, right? Where we have the strain or the characteristic strain really on the y-axis, the amplitude of the wave. On the x-axis is the frequency. And this is kind of like the picture of what we expect in the next 15 years-ish for what we'll be able to see. Right. There are a lot of other missions that I'm leaving out here. Of course, I'm leaving out Virgo. I'm leaving out a lot of other things, but this is kind of the big picture of what we'll be able to see. So LIGO has already done a great job here in the 10 to 100 hertz range, and that's let us see all of these 10 to 100 solar mass mergers. In about 15 years, LISA is going to be launched, and it's going to be there in the millihertz range. That's going to let us see these intermediate mass black holes. And then pulsar timing array all the way down at the end in the nanohertz regime is going to be looking for the inspirals, this stochastic gravitational wave background built up of all the inspirals of the supermassive black holes in the universe. It's going to be able to look for that. And actually, it's already doing that. All right, so this is kind of the picture that we have right now. And if you'll notice, there are a lot of gaps in this spectrum, right? Even in 15 years, we really won't be able to cover certain parts of the spectrum. Now, the part between LISA and LIGO, we think will probably be covered. There are a lot of ideas for how to do this, a lot of proposals. So that'll probably happen. However, between LISA and pulsar timing array, this is a bigger problem, right? If we were to try to build a laser interferometer like LISA or LIGO in this range, we'd need to build it with arms that are out to Mars's orbit, which is definitely beyond our technological capabilities right now. And there are a few other ideas for things we could do. So, we could put atomic clocks on asteroids, and that's super cool and would probably work. But again, it's a little bit beyond our current technology. So what I want to talk about today is one way to actually get some measurements in this frequency band for free with telescopes that we're already going to be launching without changing any survey parameters. And so this is the basics of these papers that we've been writing. So before I really talk about that, I want to talk a little more just to remind you all about how pulsar timing arrays work, because the idea here is really similar. So the idea behind pulsar timing arrays is that we have a gravitational wave that comes through the Earth. It distorts the space-time at Earth. And when it does that, it changes distances to pulsars. So pulsars are rapidly spinning neutron stars. They spin as quickly as one rotation every millisecond, and they emit powerful radio waves when they do that. So we can monitor these radio waves, and because these pulsars spin very precisely, they're very precise clocks essentially, then we know that we're going to be getting these radio waves, for example, once every millisecond. But if a gravitational wave were to come through and distort that space-time, maybe make it a little bit longer between us and the pulsar, then a pulse would come in a little bit later than normal. And if a gravitational wave contracts that distance, it comes in a little bit early. And so what pulsar timing arrays are doing is they're monitoring all of these pulsars on the sky, and they're looking for a correlated delay or early arrival of these signals. And they're looking for a very specific pattern that I'm going to talk about later because it's relevant to later parts of the talk. But for now, just know that they're looking for this correlated pattern. Okay, so the idea here is very similar, right? Where we're looking for correlated changes in distances that are caused by a gravitational wave that comes through the Earth. But now instead of looking at changes along the line of sight, we're looking at the transverse distance, so on the sky. And so when this happens, it appears to us as if stars have moved. They haven't really, it's just this distortion in space-time at Earth. And so here is a cartoon of what this would look like, right? If you're looking up at the northern hemisphere and all of these blue dots are stars, your red star is where a gravitational wave source has just gone off. Then these blue lines are where the stars would wobble along as the gravitational wave came through the Earth. And it's essentially like a quadrupole pattern on the sky. So the exact equation that describes it in its GR glory is here. And so we have here n sub I is the star position on the sky, Q is the gravitational wave source position, and H is the strain at Earth. Because again, this is caused by a gravitational wave coming through the Earth and producing correlated changes. Now, this idea is not new. I'm sure, as you can see at the bottom there, I'm citing a paper from about 10 years ago for this equation. And of course, there have been a ton of papers out looking at trying to observe this astrometric pattern with Gaia. What is new and what we realized is that you don't need Gaia to do this, right? So before we thought that we needed absolute astrometry. We needed to know exactly where the stars were in 3D space. We needed their distances. What I realized is actually we just need relative astrometry, right? This is a time-dependent signal that we're looking at. So all we really need to know is that stars have changed positions between one exposure and the next. And that means we can use any old telescope, really. Well, not really. We really need three things to do this well, because this is a really, really small signal. And so if you do want to do this, three things you need are one, really excellent relative astrometry, right? You need to know that stars have changed position on the sky between one exposure and the next. And so you need to have really small pixels. Number two, you need a large number of stars. And again, this is really just for statistical power. Because this is that correlated signal amongst all your stars, you really win by just having a lot of stars. And three, you need a high frequency of observations. And this is, again, for statistical power, but also just to get you in that band between LISA and pulsar timing array. So luckily for us, that band between LISA and pulsar timing array is actually a really common band for a lot of telescope surveys. It's in this, hours to a year gap in frequencies. And that's really common for most telescope surveys. And in particular, there's one that's going to be launching that we think is going to be perfect for this. So this is the Nancy Grace Roman Space Telescope. It was formerly known as WFIR, so you might have heard of it from that name, but it was renamed 2 years ago after Nancy Grace Roman, who's shown at the bottom right there. And she was NASA's first chief astronomer, and she was also really instrumental in getting the Hubble Space Telescope to launch. And so it's great that this is named after her because it has the same resolution as Hubble, but it has a field of view 100 times larger. And so that means for any one of its exposures, you need to have Hubble take 100 different exposures to equal that same sky area. All right, so Roman is going to be launching no later than 2027 is the official word right now. And it's planning to complete multiple surveys. So you might have heard of its Galaxy survey. So it's doing this to measure dark energy properties. I think Tessa talked about some of this earlier today. Supernovae survey to try to measure the expansion of the universe, so to measure the Hubble constant, and a microlensing survey to try to find planets. And so the idea there is that they're looking for momentary brightening of stars as a planet passes in front and lenses the star behind it. And it's actually this last one that is perfect for gravitational waves. So Roman's Galactic Bulge Time Domain Survey is the name of this microlensing survey. And the idea is that they're looking at the galactic center. So at the top right here is a picture of the galactic plane as taken by Gaia. And if you zoom in on the center here and blow this up in galactic latitude and longitude, then these black rectangles are where this survey is going to be looking. So the idea is it's looking just off the center of the galactic center. The reason for this is two. One is that towards the galactic center, you get a lot more stars. However, you don't want to look right at the galactic center because there's a ton of dust, and the extinction from the dust is shown here in red. Okay, so the idea is to try to look for as many stars as possible and monitor them for a while for this survey. And so actually this gives us everything that we want for gravitational waves. We're going to monitor 10 to the 8 stars with this. It's going to have really excellent relative astrometry. And this is just for Roman, right? It has Hubble resolution. So it's 1.1 milliarc seconds for Roman per image. And it's going to take 41,000 images of each star over 5 years. And so this actually gets us everything that we want. Now, how good is it really? We could do a really quick order of magnitude estimate. So our sensitivity to the gravitational waves, to the strain, is going to go as how well we can tell that any stars have moved between two exposures. That's just from the equation I showed before. And so that means our strain sensitivity is about something like our astrometric precision divided by the square root of the number of measurements that we make, the number of stars times the number of measurements of each star. And the signal that we're looking for in this case is a single binary. I'll talk about the background in a little bit, but for a single binary, that means that our frequency, that our signal is going to go as the frequency of the gravitational waves to the 2/3 times the chirp mass to the 5/3 over the distance. Okay, so if we bring up our previous plot that had all of the different, that had the gravitational wave spectrum on it, and we zoom in between LISA and pulsar timing array, and we do this quick estimate, this is what we find for Roman. Now, one caveat here is that I'm not really plotting apples to apples here. I'm plotting Roman's strain as a function of frequency. It is not the characteristic strain, which is what I'm plotting for everything else. I'll come back to that later and plot the real version. This is just for an order of magnitude estimate. But you'll see that the frequency range is really exactly where we want it without changing anything about the survey itself. It's right there between LISA and pulsar timing array. The sensitivity doesn't look great, and a lot of that is because I'm plotting this as strain and not characteristic strain. So just to give a little more context, we can plot in strain what a merger, a 10 to the 7.5 solar mass merger at 50 megaparsecs, for example, looks like as it traverses in strain versus frequency, and this is that. So you would see that Roman would actually have sensitivity to an object like that, which is really cool, right? Something I forgot to mention earlier is, a lot of these really large supermassive black holes, the 10 to the 8, 10 to the 9 solar mass black holes, we're not going to see them merge unless we have sensitivity in this band. And so Roman shows that it could see mergers in this band. At least that's with this order of magnitude estimate. Now, when you start to do things correctly, the story changes a little bit. So I need to go back a little bit to this earlier idea of we're looking up at this hemisphere. Here it's the same sort of picture, except now we're looking directly above us. And sorry, now we're looking at the hemisphere again, but the gravitational wave source is directly above us here. And the black and blue lines are just giving you that change in star positions for different polarizations of the gravitational wave. Okay, so this is what you see if you see a full hemisphere. But Roman, or really most telescope surveys, do not measure the entire hemisphere in any one exposure. They see just some small fraction of it. And in particular for Roman, the field of view is half a degree by half a degree. And so if you pull that up and you look at what the signal looks like, this is it. So to remind you what this is you take an image somewhere, you go and do something else, and you come back and take another image, and then you plot the difference in star positions between those two images. So this here is unfortunately totally degenerate with pointing error. So that's the idea that when you came back the second time, you pointed your telescope just a little bit too low. And so you thought that your stars all moved up, but really it was just you made a mistake and pointed your telescope a little bit too low. And because this is such a small signal, it's not really clear that we can actually ever fix this problem for a survey like Roman, right? At least with all of the instruments that Roman has and its capabilities. Luckily for us, there is a way around this, and that is you could just subtract the mean signal across your field of view. When you do that, you get this sort of pattern on the sky. Now, this is something that is, that we could hope to see and that isn't degenerate with any other instrument systematics that we know of. However, it is 100 times less powerful than the full signal. And so that changes our sensitivity curves quite a bit. And so if you want to know, if you do this fully with an MCMC and all of that, this is what you find for the 2 sigma sensitivity for Roman in chirp mass of a binary versus the frequency. And each of these different colors are showing different distances from us. Since there's a degeneracy between the mass and the distance, we have to fix one of these. So if you fix the distance, these are the masses and frequencies that we're able to see. And so you'll notice we're able to see something like a 10 to the 8 solar mass binary with 10 to the minus at a 10 to the minus 5 frequency and at 1 megaparsec, which isn't great, right? 1 megaparsec is not very far. It's only a little bit past the Andromeda galaxy. And so it's unclear that Roman will actually be able to see any binaries unless we are very, very lucky, right? We would need to be lucky enough to have one of these pretty rare systems within, at least 10 megaparsecs. Now, the story does get a little bit better if we're able to make a few other assumptions. So for example, if Roman does about 10 times better than it's expected to, and right now the detectors are testing at that level, this 0.11 milliarc seconds per image, then we could go out to 100 megaparsecs, at which point it's a bit of a better guess that we could actually see something here. And if we're able to figure out this pointing error degeneracy, we could look all the way out to 1 gigaparsec, and then we definitely see something. Now, I've painted a bit of a bleak picture, so you might be wondering why I'm still talking about this. The main reason is that this first paper that we did only looked at one binary systems, right? But really, we expect there to be a whole population of these supermassive black holes. And so we do expect to see something, right? And this is, the gravitational wave background that I mentioned earlier that pulsar timing array is looking for. Roman could look for this too. We're going to look for a slightly different population than what pulsar timing arrays are looking for. This will be a slightly less massive population, but it is still expected to have a background. Okay, so let's talk a little more about the background and how we would actually try to observe this, right? So the background itself is normally defined by its characteristic strain. And the way you get this is you take your strain as a function of time, you Fourier transform it into strain as a function of frequency, you take the 2-point function and you get this S sub h, which is your power spectrum of your signal. And then you make this dimensionless by multiplying it by the frequency and taking the square root. This is your characteristic strain. And so this is what's normally used whenever we talk about the background and how strong it is. And so when we're looking for a background, this is a stochastic signal overall, right? And so we can't look at it in the same way that we did these binaries where we use templates to try to fit that out. Now we need to use some more different statistical tools. And the two main ones that we want to use here are the angular power spectrum and the frequency power spectrum, right? So decomposing this map here into spherical harmonics and then analyzing this strain as a function of frequency power law, essentially. And whenever we're looking for the background, and this is true for pulsar timing array, and I'll talk about that in a second, whenever we're looking for the background, we really need both of these to make a confident detection of the background. So this is what pulsar timing arrays do. And so these plots here are from IPTA's recent paper this year, where they've seen hints of the background. They're able to see this characteristic strain as a function of frequency. They see some amplitude here. They make a detection of the amplitude being at like something 10 to the minus 14 and a half or so. And so that's great, but they don't yet see that angular power spectrum that they expect. So this is on the right-hand side. This is their power spectrum essentially of their timing residuals, or this is the cross correlation. And so what they're looking for here, and this is in general for most gravitational wave signals, what we want is the quadrupole moment. Here, this is called the Hellings-Downs curve for pulsar timing arrays. And so far, they have not seen that. They see evidence for a monopole, an overall noise that's shared amongst all their pulsars, but they don't yet see this quadrupole that would really make it clear that it's definitely gravitational waves. And so for this astrometry signature, we want to do the same sort of thing, right? We want to see if we could detect both the frequency and the angular power spectrum. So for the angular power spectrum, the way that we would do this is similar to how CMB polarization works, right? We want to decompose these changes in star positions into spherical harmonics. However, in this case, unlike CMB polarization, we're going to do it using spin one spherical harmonics, since these are spin one quantities, they're vectors on the sky. And so we can do that and we get these coefficients, the ELMs and the BLMs, and roughly speaking, the E modes, as they're called, give you the divergence-like signals, and the B modes give you the curl-like power. And so you can take your 2-point function of these E and B coefficients and you get your power spectrum in E and B modes. And previous work has shown that this can be related to the gravitational wave background from supermassive black hole inspirals, as is shown here. And so it's essentially an integral over your characteristic strain. And it's something where both the E and B modes actually have the same power, and they both fall off really steeply with L. So as you go to smaller scales, the power falls off as 1 over L to the 6. For photometric surveys, we can work out what the noise properties should be in these E and B mode signals. And it ends up being pretty similar, actually, to the earlier naive order of magnitude estimate with an extra 2 pi just for normalization. However, there's an extra catch, and that's that these surveys don't view the whole sky at any one time. They actually view just a small part of the sky. And so again, we have to make these adjustments to that. And so that's shown there. And the upshot here is that actually when you have small surveys, such as the Roman Space Telescope or even things up to 10 degrees on each side, you're going to lose a lot of SNR when you're actually trying to look for these angular power spectra. In fact, we expect, for example, for a 2 degree by 2 degree survey, we're only going to have about 10 to the minus 11 of the signal to noise that we would have if we were able to view the entire sky. And so what we found here was that we don't expect any surveys that are just viewing a small part of the sky at any one time to be able to measure the angular power spectrum, probably ever. That changes if you are able to view a much larger part of the sky, but at least for something like Roman, this is impossible. However, the frequency power spectrum is a much better story here. So here what you can do is write your characteristic strain as a power law and solve for the amplitude, assuming that the frequency goes to the minus 2/3, which is what we expect for supermassive black holes. Of course, that power law is different for any other physics that you want to look for. And the noise for that for these surveys, for a telescope survey with finite time sampling and assuming that you're sampling at the same cadence all the time, it looks like this. So there's some correction factor to our original approximation. And so our final actual sensitivity curve for a characteristic for a gravitational wave background is here in characteristic strain versus frequency. And so in gray, you have the pulsar timing array and LISA curves as before. In red is this pulsar timing array possible signal that they have seen. So it's at that amplitude and assuming the frequency to the minus 2/3, and we've extrapolated down to lower frequencies. And you'll see that Roman here would be able to see it. Now, we have a huge range here in what Roman would be able to see, and this is us just trying to correct for the fact that maybe we have to take out the mean signal from our field of view every time we actually do this analysis and not just for the binaries. And since we saw that that was about 100 times less powerful signal, this is what we're showing here in our bands. Really, we expect it to be somewhere in the middle here, right? We expect there to be some degradation from having to subtract the mean across the field of view, but also for a gravitational wave background, you don't necessarily expect there to be a large mean across your field of view. And so there's going to be, the real curve will be somewhere in the middle here. But either way, we do expect that we would be able to see the same signal that pulsar timing array is seeing, but at these higher frequencies for slightly lower mass black holes. So as a quick wrap up here, we think that relative astrometry is one way that will help us bridge this gap between LISA and pulsar timing array. And it's a way that we can do it for free with telescopes that are coming out in the next 5 years. So we're really excited about that. Unfortunately for Roman exactly, we don't think that it's going to be able to look for any individual binaries, and it won't be able to see this angular power spectrum. But we think that it should have sensitivity to the frequency power spectrum of the gravitational wave background. One extra note that isn't on this slide is that, again, this can work for any telescope. And so we are currently working on doing some analysis on older data that we think will be as good or better than Roman. And so we hope to have some interesting results on this soon. All right, with that, I'm happy to take any questions.
Great, thanks for the very interesting talk. So are there any questions? If you have questions, just unmute yourself and ask.
Well, I might have one, if I may. So
yeah, sure.
What you're showing, so this is, well, HC. So this is something that I would call instantaneous sensitivity, in the sense that this is just, let's say, the noise level, right, of the experiment, roughly.
No, so this is integrated across. This is the characteristic strain.
It's integrated, okay. But where I'm going with this is that for other experiments, you take this and you can go to, say, power law integrated sensitivity.
Yes.
Right, but can you do this also with astrometric surveys?
I don't see why not. What exactly?
Well, because the thing is,
I mean,
the way LIGO does it, for example, is they have two devices, and the noise should be uncorrelated. So the correlated part would be, that's why you integrate over time. But here we have only one, let's say, set of objects, right?
But each object itself is a separate detector in a sense, right? In some sense, we have 10 to the 8 arms out to each star. Now, you're right that there is an overall systematic noise from the telescope motion itself. But in the end, we do have 10 to the 8 other arms that we're cross-correlating in a sense. That is what this analysis is.
Oh, okay.
Yeah, there are other systematic errors we have to deal with. But
okay, but it's still better than one could have thought, naively, let's say.
yeah, right. yeah.
Okay,
Good
thanks.
question. Thank you.
Are there other questions? Tessa, please.
Just to check, maybe a follow-up or to check I understood the result of the previous question, slightly different, but the pointing error then, could that not be removed by using multiple space telescopes, which is quite expensive, but is that what we're saying?
Yeah, I mean, yes, overall. So I guess there were 2 parts, but also hi, Tessa. So there were 2 parts where, you know, in some sense, within the point, like if you just took your telescope and you only stared at one spot and you didn't move it, you wouldn't have the pointing error, and you would be able to use like the cross correlation amongst all the star positions to basically zero out any noise amongst any one star. And so that helps you. But you're right, for the pointing error overall, for any telescope that is looking at multiple spots on the sky, you do want like a second telescope that's essentially looking at another spot. You'd probably want it on the same spacecraft, actually, and separated by like 90 degrees or so. That would be the best way to do this.
And so anything that's planning to fly in the next 5 years, like Euclid, are they of any use, or it's not got the right setup? No. Okay.
No, Euclid doesn't work because it also doesn't have a survey that's looking at the galactic center at anywhere with really high source density of point sources.
Okay, we'll just have to get funding for a second.
Yeah, we'll just need to launch some more.
Thanks.
Mm-hmm. So, well, I have one more question, which is related. So if you don't want to go for another telescope, is there something you could modify in this Roman telescope to, you know, make the sensitivity better for this aim, or?
Yeah. So, I mean, the point and stare approach where you stay on the same part. So before I showed that Roman's going to be looking at like 7 different spots near the galactic center. So if they just stared at one spot instead of going between all 7 and just sat on it for the entire time of that survey, that would basically take out the pointing error that we're talking about. And so that
yeah,
would
but
really
I guess
help.
that's something you cannot do, right? Because then you don't scan.
Yeah, then the planet
points,
people
right?
will be mad at us. Yeah, there's certain issues with that you know, other astronomy folks will be upset about. But yeah.
Okay, I see. Thanks. Any other questions? I don't think I hear anyone else. So thanks, Chris, again for a very nice talk. And let's move on to the next talk of this session, actually the last one. So could you share your slides, please?
Yes, I can share my screen. Okay. Hello, everyone. So since this is the last talk, I will try to make things simple. I will skip many details and mainly focus on the physical pictures. So in this talk, I will try to talk about a revisit of the mergers of primordial black holes. And so first, I would talk about what primordial black holes are. Since several speakers today and in the past few days have talked about this, I will keep it short. And then I will discuss how the merger rate of primordial black hole binaries was calculated and see if we can have some new aspects from the calculations. And then I will show the resulting gravitational radiation background from these mergers. And lastly, if time allows, I will talk about the effect of mass accretion on the PBHs and how this could lead to a different gravitational radiation background spectrum. So primordial black holes, or PBHs, are hypothetical black holes formed in the early universe before any large-scale structures like galaxies. Depending on the model, a PBH can have a huge range of mass. It could be as small as the Planck mass, or it could be much heavier than the sun. The solar mass is about 10 to the 33 grams. Slightly heavier than the solar mass, we have the astrophysical black holes. And even slightly heavier, we have LIGO black holes, which have masses around 10 to 100 solar masses. And now we have around 150 LIGO black holes. And this is one of the motivations of the study of PBHs, because these LIGO black holes are slightly heavier than what people would expect from astrophysical black holes. So it's possible that some of them are actually primordial black holes. And then we have these supermassive black holes at the center of most galaxies. So they have huge masses, and it's hard to explain them from the evolution of astrophysical black holes. And since PBHs can have huge mass when they were born, so they could be the seeds of supermassive black holes. And then it has long been suggested that PBHs is a candidate of dark matter because they are dark and they behave like matter. But we already have many observational constraints on PBHs as dark matter. So here the horizontal axis is the black hole mass. Here we assume that all black holes are of the same mass. And the y-axis is the fraction of dark matter in PBHs. If it's 1, it means that all dark matter can be explained by PBHs. We can see we still have a window here. But today I'm going to talk about large black holes, PBHs. And here's the solar mass. And even if these black holes can only make up a small fraction of the dark matter, they could still be interesting. For example, they could be used to explain the LIGO events. So the physical picture of the formation of PBH binary is actually very simple. Regardless of the mechanisms of PBH formation, so we know we have a lot of mechanisms. If we just assume that these PBHs are randomly distributed in space in the early universe, then they typically do not interact with each other. The number density of PBHs simply gets diluted by cosmic expansion. However, it's possible, and we can calculate the probability, that two black holes are formed so close to each other that their gravitational attraction could defeat the cosmic expansion, could defeat the Hubble flow, so that they would come close to each other and form a bound system. If there's no disturbance from the environment, these two black holes will simply experience a head-on collision. However, we have the environment, right? We have other black holes, we have the density fluctuations in the universe. And these two black holes would eventually form a binary system. And they would rotate around each other for maybe for a long time, emitting gravitational radiation, and eventually they would merge. If the coalescence time, so these binaries are formed in the very early universe during the radiation era. If the coalescence time of the binaries is of the age, approximately of the age of the universe, that they would merge today and could possibly be detected by LIGO. If these mergers took place a long time ago at early times, we cannot detect these individual signals, but these mergers can contribute to the background. Now, when do two neighboring black holes decouple from the Hubble flow? So first of all, if there's no cosmic expansion, then we have this free fall time. So if we only have these two black holes, they will fall into each other within some time, and this is called a free fall time. On the other hand, we have the Hubble time, which characterizes the expansion of the universe. initially the Hubble time is small, and the free fall time is larger than the Hubble time. At some point, the free fall time could be smaller than the Hubble time. This is when the expansion of the universe becomes insignificant. And this is when we call these two black holes decouple from the Hubble flow, and the binary forms at this time. When the binary forms, the physical separation of the two black holes can be regarded as the semi-major axis of the elliptical orbit, A, here. We can also estimate the eccentricity of this orbit. This can be done by taking into account the environment disturbance, for example, the effects from other black holes and from density fluctuations in the universe. Typically, this disturbance is quite weak, so these binaries are typically quite eccentric. Then each orbit can be characterized by these two numbers, A and E. And then we can find the coalescence time from A and E. This is given by the so-called Peters formula. And it looks like this. The Peters formula was calculated, roughly speaking, as follows. So if we consider a black hole rotating around, running in this orbit, after one period, we have a slight energy loss from the emission of gravitational radiation. And the semi-major axis decreases a little bit. And if we go around for many periods, then we can actually calculate the rate of change of this semi-major axis. And so we can find out when it would decrease from the initial value to 0. And that's when these two black holes merge. So this is how the Peters formula was calculated. And then by studying the probability distribution of the black holes, we can find the distribution as a function of A and E. And then by the Peters formula, we can translate this into the probability of time, which is the coalescence time. This is the primordial black hole's merger rate. And we can go through all these calculations. It's a bit tedious, but quite straightforward. And the result is the follows. It's calculated in this paper in 2016. And here, the horizontal axis is the cosmic time, and the y-axis is the number of merger events within a Hubble time. And we can see that there's a transition time here, Tc, and I'm not going to talk about the details why we have this transition time here, but this Tc is given by this formula. Before Tc, the merger rate increases, and after it decreases. And we still have this lost time. This is the time when the last binary in the universe merge. And this is typically a huge number. So let's take a look at an example. So if we have PBHs of mass around 10 solar masses, and the fraction of and this F, which is the fraction of dark matter in PBHs, is about 0.1%, then this Tc is around 10 to the 19 seconds, which is much larger than the current age of the universe. What's interesting is that these two parameters can actually be used to explain the LIGO events, and it's proposed in this paper. And what's interesting is that this paper was written only after one single event of the LIGO detection, but this conclusion still holds. So if we have some PBHs with masses around 10 solar masses, maybe 30 solar masses, and the fraction is about 0.1%, then these PBHs can be used to explain the LIGO events. Okay. So this is the how people used to calculate the merger rate, and this is all based on the Peters formula. Now you may notice something interesting from the Peters formula. If the eccentricity goes to 1, the coalescence time goes to 0. But this doesn't make sense, right? So initially, these two black holes are separated by a long distance. So if the disturbance is very weak and the orbit is very eccentric, it doesn't make sense that they would merge immediately, right? The coalescence time predicted by the Peters formula is 0. So it takes 0 time for them to merge. It doesn't make sense, right? So it at least takes the free fall time for them to merge. So they may come close to each other and they may do something very complicated, but the merger time is at least the free fall time. So we have this problem because the coalescence time can be estimated by the Peters formula only if the Peters formula, the value given by the Peters formula, it's larger than the free fall time. So the free fall time is, roughly speaking, 1 period. As we mentioned, the Peters formula was calculated by assuming that the black hole runs in the orbit for many periods. But it's possible that the coalescence time is actually dominated by the free fall time. So roughly speaking, I would estimate that the coalescence time should be something like this. It's the sum of these two, depending on which one dominates. Right, so the coalescence time is no longer given just by the Peters formula. We have an additional term. And then we can calculate the merger rate once again from the distribution of the orbit. And then we translate this into the merger rate, P of t. And the result is the follows. So we can see that we could have an enhancement here at this transition time. So previously we have this increases here and there's a smooth transition and then decreases. But now as we go back in time, we have an enhancement here. Physically, the enhancement comes from some of the last group of binaries. So it can be shown that all these PBH binaries were formed during the radiation era. So the last group of binaries are formed close to the dust radiation equality. And some of them, for some of them, the coalescence time is dominated by the free fall time. And all of them will merge almost at the same time. And that's what causes the enhancement. So I will skip many details and show you the main conclusions here. So this tells us that some PBH binaries were formed much later than previously expected. Because previously, when people used the Peters formula, some binaries merge within 0 time, but actually it takes at least the free fall time, right? So they were formed later than previously expected. Another conclusion is that this effect is only significant for huge black holes. So for PBHs around 10 or 100 solar masses, they are not affected by this free fall effect. It's only significant for PBHs with mass much larger than, say, 10 to the 5 solar masses. Then from this enhancement in merger rate, we can calculate the resulting gravitational radiation background. So these are some previous results of the spectrum, gravitational radiation background spectrum from small PBHs. And the x-axis is the frequency and the y-axis is the density spectrum. And here we only show some results from very small black holes, some black holes with masses less than 100 solar masses. And here we have pulsar timing array, we have LISA here, and LIGO is here. And the thing to notice is that there's only one peak, right? And the peak is given by this formula here. However, with the free fall effect taken into account, we can calculate the modified spectrum from these PBH mergers. And these are the results. So for this small black hole, so here again, the x-axis is the frequency. And for small black holes, so this is the result from black holes of mass around 100 solar masses. There's only one peak. However, for some huge black holes, say this 10 to the 8 solar masses, we can see that it develops an extra peak. This is from the enhancement of the merger rate at early times. If we don't consider this, then we only have one peak here and it goes down. It's simply just like this blue curve here. So previously we may think, okay, if we have a fraction, so for black holes with mass around 10 to the 8 solar masses, if the fraction is 10 to the -5, then we will never see them, right? However, with this free fall effect taken into account, it's actually possible to detect such a signal. So if we don't see the signal, if we don't see this kind of background from these future probes, like UDCycle or SKA, then we would expect that more stringent constraints on PBH abundance. And here we'll only show, we are only interested in huge black holes, so we will only show the constraints here. So these are the current constraints. I will compare with these 4 regions, 1, 2, 3, 4. In the next picture, so we have this 1, 2, 3, 4, the gray and 3 red regions. And this is the current constraint. If we don't discover any gravitational radiation background in the future, then we could actually constrain the abundance of PBHs to this blue region. So this could be some new constraint, and it will be an independent constraint compared to other constraints. Okay. So this is the effect of free fall time and how it would lead to a different gravitational radiation background spectrum. And now I would talk a little bit about mass accretion, but this is quite model dependent, so I will only focus on the toy model. And we can see how this could also affect the radiation background spectrum. So PBHs can absorb the surrounding gas and dark matter during the dust-dominated epoch and could grow by orders of magnitude. We have these accretion during the radiation era, but it's not very significant. It's only significant during the dust-dominated era. But the details of the mass accretion is very unclear. This is because the interactions between the black holes and the environment is very complicated. So we would consider mass accretion that takes place at around 10 to the 16 seconds. So before that, the cosmic expansion is very fast, so mass accretion is not significant. And after this time, we have structure formation, which also suppresses the accretion rate. So roughly speaking, the significant accretion takes place around this time. So with the change of the black hole mass, the binary orbit also changes. And this, of course, would change the PBH merger rate. So it was shown in this paper that the rate of change of the semi-major axis and the rate of change of the black hole mass obeys this relation. And we can see that this can lead us to A is proportional to m to the -3. In the meantime, the eccentricity remains constant. If we take a look at the Peters formula, the coalescence time is proportional to A to the 4 divided by m cubed. Since A is proportional to m to the -3, so this is m to the -12, so the whole thing would be m to the -15. This means that the coalescence time is very sensitive to the mass change. If the original coalescence time is t, then after accretion, the coalescence time is this, where this mf is the black hole mass after accretion and mi is before accretion. We have this huge power here. So this could be a very tiny number. This tells us that if we take into account the effect of mass accretion, the coalescence time can actually decreases by many orders, can decrease by many orders of magnitude. Let's take a look at an example. So if we don't consider mass accretion, if before or after the accretion, the black hole mass is around 100 solar masses, then we have this T last, which is the coalescence time of the last binary in the universe. And it's 10 to the 39 seconds. So it's a huge number. However, if we consider mass accretion, if the mass increases from 100 solar masses to 10,000 solar masses, then we can see that due to the existence of this tiny number, the coalescence time decreases to 10 to the 9 seconds. This is even much smaller than the age of the universe during the accretion. This tells us that all those binaries that should merge, so without the effect of mass accretion, that should merge between 10 to the 16 seconds to 10 to the 39 seconds would all merge during the accretion era. So this is what I call the aggregate mergers during accretion. This would certainly have some effect on the background spectrum. And so previously I showed this spectrum so I'm gonna show some a picture of the effect of mass accretion for small black holes. So before we have this blue curve for black holes with mass around 100 solar masses. And if we take into account the effect of mass accretion, we would have very different results depending on how the accretion, how much the mass grows. For example, if the mass simply grows from 100 solar masses to 200 solar masses, then the change is not very significant. It changes from the blue curve to the orange curve. However, if it increases from 100 solar masses to 300 solar masses, then we can see that the spectrum is very different. It changes from the blue curve to the green curve. We have a peak here and we have another thing here. This is because many mergers may take place during the accretion era, and only a small fraction of them would occur at the current time. So this is why this high frequency part is suppressed. So we can also consider a different case. For example, if we increase the fraction from 10 to the -7 to 10 to the -4, and the mass accretion make the black hole mass change from 100 solar masses to 250, then we can see we can develop an extra peak here, which is actually similar to this case here. And since we have increased the fraction, we can possibly detect them by future probes, such as the Einstein telescopes or Cosmic Explorer. So if in the future we see some features like this, then it's possible that this reflects the mass accretion of primordial black holes. So to conclude, the Peters formula actually underestimates the merger rate of large primordial black holes. And the gravitational radiation background spectrum from the mergers of these huge primordial black holes can develop an extra peak. If future probes do not see such a background, the fraction of dark matter in PBHs is constrained to a much smaller value within this huge mass range. And lastly, the mass accretion at redshift about 10, and the time is about 10 to 16 seconds, could significantly affect the background spectrum from these mergers. So this is all I have to share. Thank you very much for your attention.
Thank you very much for your talk. So are there questions? Okay, so I'll ask a warm-up question maybe. I wanted to ask you, because you talked about this accretion and, well, you gave us some examples, right, by how much the mass could grow, but do we understand or can we model how this happens and how to predict this number, like the
Yeah.
final mass, or
Yeah, I would say it's very hard. So this is highly model dependent. Maybe people are doing simulations about it and people have calculations about it, but typically we would expect that if we have a PBH with mass larger than 10 or 100 solar masses, then it would typically increase by orders of magnitude, but the exact number is highly uncertain. But for smaller black holes, for example, for black holes with maybe 1 solar mass, we do not expect such a huge accretion, but only for large black holes.
okay, and then are there plans for performing such simulations, like more detailed computations of that, or do you know anything about it?
That I am not sure. Yeah, I haven't thought about that.
I see.
Yeah.
Okay, and one more question. So this fraction of dark matter that is made of primordial black holes, that's model dependent, right? But are there some? Well, you showed us the plot with the constraints, right? So these are that's what we know for now, right? Or
Yeah. Yes. Right.
Okay.
Yeah. And also yeah, maybe there's 2 more dimensions, but these constraint should also so these constraints actually ignore the effect of accretion. So for example, so this gray area here, they are from the effect of mass accretion during the radiation era and how the accretion may affect the CMB. So this constraint is from high redshift, about 1,000. And these red regions are from the dynamics of the black holes. They are constrained at low redshifts. But we know that black holes within this mass range could actually increase by many orders of magnitude. So this is only the constraint for, this is not the constraint for the current black holes. This is the constraint for the black holes back in the age where the redshift is about 1,000. So this, these constraints should actually change with accretion taken into account. So
Okay,
that's, yeah, that's something, comments I would like to add.
Thanks. Any other questions for now? Or are you saving your questions for the discussion session that's coming? Okay, I don't hear any more questions, so let's thank Helen again for a nice talk. And I think we can move on to the discussion session. And I can see Laura here, who was supposed to chair this session, so I'll pass the microphone to you. Is that okay?
Of course, yeah. Thank you so much. It's a great pleasure for me to share this last session, and I first of all want to thank the organizers for putting this really great workshop together with so many different topics that are addressed here in such a broad and diverse program. So thanks a lot for that. It's a great pleasure for me to share this very last session on gravitational waves from astrophysical sources and gravitational detection principles. And I would like to welcome the plenary speakers of today that here in the panel. I will just go from left to right on my screen. I see Helen Dan from Oregon State University. Then I see Tessa Baker from Queen Mary University in London. Then Chris Pardo from Caltech in the US. And I believe that's it, if I am not mistaken. So thanks so much for joining this discussion. Also, I want to welcome everyone from the audience, and I think now it's a great time, if you have a question left from the talks that we heard before, to ask this question. If you have a question, I would like to ask you to raise your hand or just use the chat. I will then read the question and ask them to our panelists. To kick off the discussion, I would start with the first question. So I would like to hear from you. There are so many things that one can explore in gravitational wave astrophysics. What do you personally think are the most interesting avenues or ideas for the future, and what might be challenges for us? This can be from a theory side or an experimental side, depending on if you're a theorist or an experimentalist. So what do you think are most exciting things we should have a look at?
Maybe I can jump in on that one. I mean, I have a very biased view, it has to be said. But in the short term, what I would really like to see pinned down is this mass distribution that I referred to at the end of my talk. So we have, so going into the first LIGO observing run, there was basically no knowledge about that. There has now emerged definite evidence for a mass distribution that has features. So we believe there are some gaps where we don't think there are compact objects forming, and there is some kind of power law slope to the mass distribution, but all the precise details of where those gaps are, what the power laws are all kind of up in the air right now. But I think that's something exciting because it, you know, we've learned a lot already from less than 100 events. So, you know, you can imagine that maybe with just another 200, we'll start to actually pin down some of those numbers, and that goes in multiple directions. If you're an astrophysicist, that pinning down that distribution starts to tell you a lot about formation channels for compact objects, which there are a lot of ideas for. And, you know, as I said, as a cosmologist, it's really stuff that we have to get pinned down before we can do a lot of fundamental physics, because otherwise it just dominates our constraints.
Right, yeah, I totally agree. So learning more about this mass distribution is super essential, both from an astrophysical and cosmological perspective, definitely. Chris or Helen, would you like to add more to that?
One thing I would like to add is, so as Chris just mentioned, so people working on PTA haven't discovered the background, but they see something, right? But they haven't seen the Helens-Downs curve, right? But what I heard is that they are actively analyzing the latest data, and hopefully they will have some results next year, maybe. Yeah, that's what I'm excited about. Maybe they will discover something, possibly a Helens-Downs curve. I don't know.
Right. Hopefully a Helens-Downs curve. Would you be more excited about gravitational waves that tell us something about the early universe, or astrophysical sources, or independent of that? What would you like to see?
Okay, wasn't sure. Was that question for Helen? Or, okay. Yeah. Okay. I mean, sure. I think it would be really interesting if it was some early universe, but I think that it's definitely going to be supermassive black hole binary background. And kind of going back to the previous question.
Why is that?
Oh, I mean, we expect them to be there, right? It's a natural consequence of knowing that most galaxies have supermassive black holes at their centers and that galaxies merge, right? We expect there to be a background. And given that most galaxies do have these supermassive black holes, this background should be quite large, right?
What about the final parsec problem?
That's true. That could be a problem. True, but then again,
so would you be surprised that
seems to have one at the center.
So would you be surprised that if they find something and it does not agree with the background from supermassive black holes?
Yeah, I'd be pretty surprised. Yeah. Yeah.
Interesting. Yeah, I would be hoping for having my guess would also be like having background from supermassive black holes, but I would hope for supermassive black holes plus X, so that we have also like other contributions from cosmology, for example, from phase transitions, from the early universe, inflation, whatever it could be. But I agree.
Here's a question. If we saw a background and it was, attributed to supermassive black holes, population models for SMBHs are also very uncertain right now. Would it down that?
Yeah, I think it would. Actually, I was going to say, as my interesting thing was going to kind of combine both you and Helling's thing, was just to say this population models for supermassive black holes and getting a better handle of really what we actually expect there. So for two reasons, right? We want to learn more about the astrophysics of these objects. And second, so we could subtract this signal and hope to see some sort of early universe or other beyond standard model signatures in that frequency range. So there's a lot there, and there's a lot of uncertainty on the populations here.
Until you say subtract it, what one man's foreground is another man's signal. I would totally do all the waveform analysis with the supermassive black holes. That's all right. I'll take them. You can subtract them.
Okay, great. I was wondering, in regard to supermassive black holes, does dark matter play a role there? So does it play a role if my supermassive black holes have a dark matter halo, for example? Would this change the signal? If so, I think this would be an interesting probe to combine astrophysics and maybe searches for beyond standard model particle physics. And I'm not sure if people have looked into that.
There is definitely work on dark matter disks around binaries, not just supermassive ones, but around stellar mass ones as well. I'm definitely not the right person to talk at length about that, right? But it does change the waveform for sure.
Mm-hmm. Yeah, right. Right, so this I think could also be interesting to explore. And yeah, then I think we have the PTA range. There will be LISA, LIGO. Are there any specific other astrophysical objects you're interested in that you would like to explore, either to learn more about the astrophysics or to learn about extensions of gravity or dark matter physics beyond the standard model?
I think some the really light objects. So looking in this higher frequency range, I think there was a talk earlier in the session about the higher frequency range. I think that would be kind of interesting, right? We don't really expect too many astrophysical objects unless there's very light PBHs, right, at the very high frequencies. But that would be kind of fun to look there and see what's going on. Yeah. And I guess there's some neutron star and other sorts of astrophysical objects that could go up into the kilohertz range at least.
Yeah, that's correct. I know, Helen, would you like to add something to this? We talked about PBH. Would you also be interested to go to this very high frequency range?
Yeah, so I would be excited about the mass distribution of the LIGO black holes. We only have 69 events now, so around 150 black holes. So we will definitely have more in the future, and they will tell us this distribution. And what people have been working on is to explain these events by studying maybe the mix of primordial black holes and astrophysical black holes. And there are many different, because we have many different mechanisms of PBH formation, and each of them would have a very specific mass function. So if we combine this with the distribution of the astrophysical black holes, then this may give us a hint of how maybe they would rule out some PBH models, or maybe they could help explain these LIGO events. Yeah. Laura, I think
I just realized, I was just wondering when you started having, would you expect different signatures if you had a merger, and one object would be a primordial black hole and the other object would be like a standard scattered black hole or neutron star, would there be anything that could tell me, okay, one of the components is a primordial black hole?
From individual signals, I don't think so. I don't think we can tell the difference. Yeah, well, except that if we find something like Chris said, if we have very small black holes detected, then that could be PBHs. Yeah.
Right.
What about spin distributions?
So as far
Go on.
So as far as I know, the spin distribution is highly uncertain from the LIGO events, and maybe they will improve this in the future from the detection. And for primordial black holes, mostly they are expected to be spinless. So if we find something like significantly indicating a strong spin, that would, I don't know, may put some constraint on the PBH mechanisms.
Okay.
So in order to say it's a primordial black hole, we are looking for a spinless and potentially a very high object.
Relatively small spin, yes.
So another sort of way in which has been discussed for distinguishing primordial and regular black holes, which is definitely couldn't be done on individual LIGO events, but in a more futuristic scenario, would be via cross correlation with galaxies. And basically what that gives you is a sense of where are the black holes located. And basically, if you find that they correlate strongly with galaxy overdensities, so you find them in regions where you have dense clusters of galaxies, the claim is, not my work, but the claim is that means they're more likely to be astrophysical because they're forming in, you know, highly dense environments where things are streaming in. Whereas if they are uncorrelated with galaxies, so they're just happening more in the kind of filaments and kind of field galaxies, then that's more likely to indicate at least some fraction of primordial origin.
Yeah, that makes sense. Yes.
Actually, this has confused me somewhat, because we do expect like galaxies to still follow the dark matter, right? So you're still going to get a bias in some sense from your events, right? So can you really quantify the difference between the bias from like primordial black holes being slightly less clumped than normal black holes? Like, is this something we could actually tell the difference between?
Good question. So you're right that it's a bias trace of whatever, and it is difference between a bias greater than one and a bias less than one. I mean, maybe we're talking, and I would have to go look up the paper again. The one I'm thinking of is by Giulio Scelfo et al. Maybe it requires like Einstein telescope level numbers of detections, but I think they claimed at least in some highly idealized scenario it might be possible.
Cool. Thanks for the reference.
Yeah, very interesting. I also was not aware of that. Okay. So yeah, we talked about primordial black holes already, but what about other dark matter candidates or modifications of gravity? Which would you think is important there for the future to pin down the properties of dark matter or to constrain more modes of gravity?
I mean, as I was saying, this is obviously something we want to do. I mean, this is something that perhaps the LIGO scientific collaboration has been a little bit, hasn't done so much in the past, because obviously to start with, they really want to stick to the astrophysics and the kind of mainstream cosmology. So, you know, my group here is now a member of LIGO. We are gradually injecting some slightly more cosmological tests of gravity into that kind of framework. Obviously, they do have a very strong existing group in strong field tests of gravity already. So that stuff is happening and doubtless will continue. I guess one of the really hard parts from the strong field tests is, you know, building the template banks for LIGO analysis, even in GR, it's hard enough. They've kind of, you know, it's nailed down for sort of very vanilla events, but for things that start to probe more extreme regions of parameter space, like things that have non-trivial eccentricity or non-trivial spins, like the simulations and the methods are just hard enough in GR. How one, you know, going and layering deviations from GR on top of that seems an incredibly daunting task, at least right now.
Yeah, I agree. So even if you want to fit the LIGO data now and use current templates, these are really complicated. And if you look at the inspiral phase, you have to take or include post-Newtonian corrections up to very high orders. And if you want to systematically study modifications of gravity, then you have to modify the waveforms in a consistent way. And I think this is a huge challenge. And I personally also think now we have a lot of information about the inspire phase, but there is, of course, the merger phase. And with future live observations, we will also be able to look at post-merger signals, hopefully. And there's also a lot of information on the post-merger signals, but it's also really a challenge to model them accurately. And we have to go back to numerical simulations. So I think there are a lot of things then that one could do or should do first of all, modeling the astrophysical objects themselves, but I think also what you said, Tessa, to look at modifications of gravity is really a challenging task. And
so can I ask a quick follow-up question?
Of course.
So has there been much work in, like, I guess, combining, so this is the half-baked question. Okay, in like combining these waveform changes with, I guess, GW 170817. So like, could you modify the waveform enough so that you could change gravitational wave propagation and still fit the data?
Ooh. So yeah, certainly at the moment, I think what's something that's not happened is combining the kind of propagation changes that I spoke about with actual generation changes. Yeah. And the reason for that is that the two camps tend to be looking at completely different theories of gravity. So, you know, we cosmologists say, I want to solve dark energy. Here are my things that affect propagation. And they usually don't do much in the strong field regime because screening. But people who study the strong field regime deliberately pick things that come out in that environment, and they often, those theories actually don't do anything on cosmological scales. So I'm not saying it's impossible, just I'm not aware of a lot of work that sort of picks a sensible theory that does both. Obviously an argument that we sometimes make is because the cosmological phase is so much longer, if you have even small effects there, they have a very long accumulation distance, and so you might expect those to dominate, but it's a little bit flaky. You have to really prove it in a particular example. And there's certainly a good question that if the waveform generation itself was like really messed up, would you even see the signal? Would all the current matched filtering analyses just throw it out?
Yeah, that's a very good point there. Yeah, interesting. Thanks.
Can I ask a question to Tessa?
Of course.
I'm sorry if I missed it. Maybe you mentioned it in your talk. So you show the possibility of, so you show the speed of light as a function of frequency, right? So is there a reason why the cutoff should be at the LIGO band, or it's a free parameter?
So that case that I showed is a sort of ballpark estimate that comes from that work by Durham and Melville, who were the people who really pointed this out. And that's like a very heavy lifting field theory calculation that I, have to look at the paper to remember the details of. So it's not a precise prediction like that number I had on the slide, which was 260 Hertz, is not like magic. But it is based on kind of estimating the energy scales that you would need to have in your gravity theory to still do interesting things on cosmological distance scales. So ballpark estimate, I think, was the manner in which that was meant to be interpreted. So it's not quite a free parameter.
Nice. But can this be ruled out at some point?
Well, so if we had some of these LISA observations that I mentioned and we did not see any such deviation, then we would have pushed the scale of that transition, if it exists, would have to be below the LISA band. And then we could go to PDA, and I don't know what the equivalent measurements would be in PTA, but maybe we could push it down to the PTA band, at which time maybe people would say, okay, guys, enough is enough. We've tested this thing. Yeah.
I see. Thank you.
Okay, so coming back a bit to cosmology, if we want to constrain like alternative models of gravity, then we of course also can use other cosmological probes like Euclid or logical structure in general. Would this be something that you consider important to combine different observational probes to really pin down models? Or would you say one or the other is more suitable for one or the other model?
I mean, I'm trying to jump in again. I mean, the obvious answer is yes, throw all the data you can at it. At the moment, a lot of the constraints on cosmology is targeted on H naught from the gravitational wave side, and that is often done without information from Planck or the local distance measurements, so without any kind of prior, because of the tension, right? You want to get something completely independent. But you know, assuming the Hubble tension is solved somehow moving forward, you definitely want to combine that data. You're never going to measure omega m very well with gravitational waves, so it makes sense to use your CMB priors on that kind of parameter to fix some parts of your cosmology and do other things with them.
Right. But yeah, so yeah, I totally agree with that. Yeah, and also I want to come back to your statement that you made before, so that usually that people who compare with the LIGO data like GW7870, for example, that they look at the strong field regime of gravity, and the models that are excluded from there are the models that are that really have strong modifications of GR in this regime. And yeah, this is I mean, there's a lot of work has been put into this, and some models have been excluded, but going to cosmological models is also really important, and I think of new ways to constrain cosmological modifications of gravity is really important. Right. So then I kind of want to switch topic, and I want to ask a question to Chris. You told us about new possibilities to detect gravitational waves. So in a completely different frequency range. So what is your perspective? What are challenges from the experimental side or the construction side for the future?
Yeah, I mean, I'm not really an experimentalist, to be clear. And I'm really an astronomer. Okay, yeah, just to like make that very clear. All right. So I mean, I think, you know, in terms of this astrometry signal, I think right now a lot of the effort is going into like, how do we properly analyze this data? Because it is kind of a new signal in some sense, and it's different from a lot of the previous papers that had focused on Gaia. We don't have all of the information that you do if you use Gaia, and it's just a very different sort of data analysis than all of these other experiments have done. And so we're really working right now to figure out, for example, how do you even tell that you've definitively seen an actual merger versus, you know, just noise in your instrument, and these sorts of things, like what's the best estimator, the optimal estimator in some sense. And so these are the sorts of things we're working out. But, you know, in terms of the data, it's all there right now. So it's just figuring out these data analysis things. In terms of like other experiments, I think I mentioned the one about putting atomic clocks on asteroids. I really like that one just as a really fun kind of futuristic idea. And then there's a lot of ideas for what to do in the other regimes. So between like LIGO and LISA that I think are also quite interesting. There's a lot of ideas to use, for example, atom interferometers in space and just kind of, or like atomic clock networks that I think are just really cool and, you know, might be a little longer in time scale than some, you know, might be closer to LISA time scale at least, but would still give us coverage in that band and I think are quite exciting. So I think there's a lot of, right now is a really good time for just new ideas for looking for gravitational waves and helping us fill in all of these different parts. So I think it's just exciting.
I agree, because we have had the first LIGO detections now, and we know that rotation waves exist. So it's like a great time to think about more ways, other ways to detect them, to come up with good ideas. But I was always wondering if there is something interesting if you go to even higher frequencies, so beyond the gigahertz range. Like I'm not sure if there could be some interesting astrophysical sources or that we could detect in this range. I don't know.
Yeah, so I mean, if you're going all the way up to even, okay, gigahertz is really, really high. Even in the megahertz range, you know, you'd need primordial mass, you need black holes that are, you know, Jupiter sized or something like that, right? They're quite small to actually get to that. So that would be really cool. I think this regime is even more interesting for the other physics that you could look for, because we don't expect normal astrophysical objects here, right? In this megahertz or gigahertz regime, unless there are these small black holes. Then really what you could look for is things like phase transitions at really high scales. You could also try to look for these like quantum gravity sorts of signatures. There are a lot of recent papers on this. And so, you know, there's a lot of interesting signatures there that you could try to look for. I think right now, like, this is just so exciting because it's kind of one point I wanted to make about LIGO has shown us, it's almost like we're only looking in the optical band in like electromagnetic waves, right? All we've seen that is that. And we've built in some sense, really, our radio telescopes that are going to give us the radio bands, hopefully soon, right? That's this nanohertz regime. And we still have to build all of these other instruments that can see at all these other wavelengths, right? And seeing how much we've learned from electromagnetic spectrum in the last century in all the other bands, it's pretty exciting.
Right. Well, but the super high frequency part, that's usually inflation, right? Because that's high temperature. So oscillons, preheating, all of that stuff, it naturally goes to, well, above gigahertz, actually. That's where you really expect it. So I think mostly, you know, all the experts on inflation are super excited whenever you talk about high frequency gravitational wave experiments.
So do you know more about the experiments there are, if there are, or what the ideas are for those kind of experiments?
Well, I think too bad Rafael isn't here. He probably knows much more than I would. But I think they are of the, say, cavity category.
Yeah.
Right, because these are smaller and smaller devices. But as he said, the problem always is, if you want to keep, because it's all stochastic backgrounds, right? When you're going from stochastic, so just abundance to HC, there is an F to power 3. So your sensitivity should be going as F to power 3, minus 3, actually, when going from LIGO. And that's not really something that we know how to do.
Right.
Even though it's looking simpler because then it's tabletop and not 10 kilometers, but still.
But the sensitivities need to be quite high.
Yeah, right. Yeah, so this is also like a big challenge on the technology side. Actually, this is also what I think is super fascinating about gravitational wave physics at the moment. So on one hand, we have certain things we look for, so inflation, for example, and then we need to build the appropriate detectors. But it's also the other way around. We have LIGO, we will have these in the future. So we have these detectors, and we have seen something that we can now analyze. So I think for me, one of the most exciting parts is this interplay between theory and experiments. Coming back to astrophysical sources, what I also find really interesting there is that you can, on the one hand, explore astrophysical objects and their properties, but you can also look for physics beyond the standard model, so for primordial black holes, for other dark matter effects. You can look at modifications of gravity, and this is somehow unique, I think, with gravitational wave physics. It's theory and experiments, it's cosmology, it's astrophysics, it's particle physics, and all of this can be explored with gravitational waves. So this is what, to me personally, is the most fascinating thing about gravitational wave physics. It's really so broad and gives so many opportunities to explore. And yeah, in the future, we are really able to explore this whole spectrum of gravitational waves and combine knowledge from cosmology, from astrophysics. So I think this is what personally excites me the most, to really have this broad spectrum and so many opportunities to look for new physics, depending if it's physics beyond the standard model or modified gravity. Right. So maybe one other question that I have, what do you think about exotic astrophysical objects? So like, could it be that we detect something like boson stars, or stars that are made out of dark matter? Is this something that the community should look more into, or is this, yeah, what do you think about that?
Obviously, there are people who work on these things looking for scalar stars and such things, and doubtless that will continue. And I think that's part of the good thing of the, even the LIGO data does become public eventually after about 18 months or something, so people are free to go and do that. I mean, personally, for me, I guess there's so much to understand with the astrophysical things that we do know. I think that has to be, for me, that's a little bit higher priority, but that means there's a great opportunity for somebody else. Yeah, no, you're totally right. So could you elaborate a bit more what you would like to explore in the future? What are your ideas, directions? Well, okay, so something my group is working on a lot right now is the dark sirens method that I kind of hinted at in my talk. So if we fail to get a lot of electromagnetic counterparts, and we don't know, we've had 1 in 7 years, it could be that we're going to get hit with a load more, it could be they're really rare. What do we, how do we recover from that decreased expectation? Like, there was a time when standard sirens were definitely like the thing, and it's actually looking a bit like, oh, they're great, but really, you're going to wait a long time for them. So so this dark sirens method is an alternative that we're working a lot on developing. I think it's a beautiful idea. It's very complicated because you have to really understand all your galaxy data, as well as your gravitational wave data. And the hardest part is really understanding the galaxies that you don't see. So you have to have a very good model for, okay, nearby I can see all my galaxies, maybe my gravitational wave came from one of them. But as soon as you start going out in redshift, you lose galaxies. They're too small, they're faint, they're obscured. And you have to understand that really, really well in order to kind of get the correct answer from your calculations. So that's something we're looking at a lot. And a part of that is what we call weightings. So trying to understand, are there some types of galaxy that are more likely to host gravitational wave events than others? Does it correlate
yeah,
with size, with stellar mass, with star formation rate, for example? No one really knows right now.
How do you approach that? How do you find out more about that?
Yeah, so what we really need, ironically, is more standard sirens, because if we have a standard siren, those cases we know which galaxy it comes from, and then independent of the standard siren science, you can start to build up a picture. Oh, you know, the hosts tend to look like this. Other than that, there's astrophysical models people can build, but it will ultimately depend on kind of, you know, modeling of binary formation channels. If you have a galaxy with a lot of globular clusters, very dense environments, that's one formation channel for compact objects. But we don't know right now which of those formation channels are accurate. So I feel like there's all these pieces of the puzzle that are all really independent and tangled together. It is quite hard to like move one forward because it depends on you moving all the other pieces forward at the same time.
Yeah, I totally agree with that. So what you mentioned, there are so many uncertainties in astrophysical models that play a role, of course, if you want to learn something about cosmological models from dark sirens. And I think this is also one big challenge that basically you need to bring two communities together. And if you want to search for physics beyond the standard model with gravitational waves and astrophysics, then this is really the astrophysical community and the cosmological community that has to come together. And I agree that often things depend on each other, and that this is a huge challenge.
Can I ask Tessa a follow-up question about this dark siren
Sure.
approach? So there was a paper by Emery, Trott, and Dragan Huderer about how you can never, this doesn't work, right? All you're going to get back is your galaxy catalog. And honestly, I found it to be very convincing. So I was wondering what you thought about that.
Yeah, I'm probably not allowed to say much about this because then I start speaking on behalf of the LIGO scientific collaboration. Let us just say we are very aware of the paper. There has been a lot of discussion backwards and forwards, trying to understand what methodological differences are being implemented, why they are getting very different results. And you can expect to see some kind of written version of that dialogue appearing at some point in the future. More than that, I cannot say.
Sounds fun. All right, thank you.
Sorry. Yeah, thank you very much. I was wondering, Helen, if you also see this challenge that Tessa described. So if you want to push forward with primordial black holes, there are also a lot of astrophysical uncertainties that fold in with that.
Not much. I don't have more comments on that. Yeah. Well, but I do want to mention one thing. It's totally unrelated. It's people found magnetic fields in the void. And this needs some explanation. So this might be exotic or not, but people may try to use primordial magnetic fields to explain these. That could be something interesting in the future. So we see something already, but it's hard to explain them with the standard picture. So that could be something interesting.
Hey, I haven't heard about that. So what do people think? Where is, so you said this are magnetic fields of primordial origin.
So Fermi found some magnetic fields in the void, and it's hard to produce them from the galactic intrinsic interactions.
Yes.
So they cannot be so one suggestion is that they could be primordial, and there are many mechanisms of primordial magnetic fields, and I think people are actively working on that, maybe from phase transition or from inflation. Yeah.
Yeah, that's true.
In-
We tried to do that at some point from a phase transition. But I think there are a lot more papers trying to do it with inflation. Yeah, although I think there were also some bounds, but there was one paper by Kohei Kamada who was claiming that somehow if you generate primordial magnetic fields that are strong enough to give you this observed signal, but you do that before electroweak symmetry breaking, you run into problems with other observables. But I don't really, well, that paper's been out for a long time. And it doesn't seem to stop the people working on inflationary sources. So,
I'm sorry, which paper were you referring to?
let me try and find it. Well, don't just wait for me. It might take a second.
Okay, yeah. I was going to say that, yeah, okay. Once you have found it, you can paste it in the chat. But so then, if I understood correctly, so you have this primordial black holes, and if they are associated to inflation and phase transitions, it might be also interesting to then look for gravitational wave signatures at the same time, right? So that you have two observables. But yeah, it would be interesting to see also, Marek, what the conflicting, what the conflicts are. You said that some observables are not, or that with these models that Kohei Kamada studied, you get conflicts with some other observables. So it would be interesting to see what these are.
Yeah. I'll find it eventually.
Yeah, no worries. So look at this later.
No worries.
But yeah, I mean, I haven't heard about that, and I think it's a very interesting idea to yeah, look at those. This is something I think in general, like if you have different observables that you can combine, is really important to make progress. And we had similar conclusion in this direction. Great. Okay. Maybe it's now a good time to ask if there are any more questions or comments from the audience. If there is something that you want to mention. You can either raise your hand or put the question in the chat, and then I'll read it and ask it to our panelists. All right. This doesn't seem to be the case at the moment. Is there anything that you would like to mention, Tessa, Chris, or Helen, that you think would be important to drive this field forward in the future?
I think we've sauntered through quite a good wide range of topics already.
Yes, I agree. We talked about we went from PTAs to LISA to LIGO to larger frequencies. Talked about astrophysical objects and cosmological or ideas to explore cosmology. Yeah. I don't know, Mark, but do you think we could stop here and have a short break?
I think so, yeah. So I just put the paper in the chat if you want to take it.
Perfect. Okay.
Right. Yeah,
Oh, I
bound
see.
to curvature constraints. So that's the problem. You produce some structure in baryons if you have magnetic fields. I'm not really sure. Well, again, I'm not that much of an expert, although that is a very active field at the moment. In fact, like quite recently, there was this paper saying that the scaling of primordial magnetic fields is different than people thought. From Oxford, maybe. Let me.
Oh yeah, that one's interesting. Yes, they found a new constant, right? Found
Yeah,
new
exactly.
conserved quantity from the helicity.
Ah,
Yeah.
okay. What is
Okay.
this conserved quantity?
They have a name for that. I don't remember. So they found this new conserved quantity. So they found that you have this even if the helicity of the magnetic field is 0.
Okay.
That's quite interesting. So for after decades, they found this new conserved quantity, and it seems that people have confirmed this in simulations.
Oh wow. Okay.
Yeah.
Could you please? This is
put
the
the
paper.
Well, it's at least those are the people, the David Hosking and his advisor, I think. Yeah, but it's true that there was, because that's also what we got years ago before any of this appeared, that essentially to have any primordial source give you the background that we're observing, you needed to have, well, some chirality. Or yeah, because then it scales slower. There's some conserved quantity in the background. But if you didn't, then it decayed fast, and there was very little hope, well, to produce the observations you had.
Right.
But they're now saying that it scales slightly slower,
Yes.
improving the
Right.
the outlook for all the sources. Because it's also true that it's not that easy to produce chiral magnetic fields.
Yes, that's right. Yeah.
Yeah, so in a phase transition, that's sort of possible, but well, we checked that the fraction of chirality you would need was order 1-ish. I mean, maybe 0.1, but still that counts as order 1. And the only thing that we know that will be generated is coming from, let's say, it's kind of like the baryon asymmetry. So it's more like 10 to minus 11-ish. So it's not, there is another source. It doesn't look very.
You need to add something very exotic in the Lagrangian to produce the chirality.
What, for example, are the studies or other models that have been tried out?
Can you repeat that? What analysis are you asking?
No, I was wondering, I think Alan said that you have to add something very exotic to the Lagrangian. I was wondering what this could be, if there are studies that have added something to the Lagrangian.
For example, you add a Siemens term to the standard model Lagrangian, you may create chirality, and that may in the magnetic fields, but it's there's no motivation for that. Yeah, I don't know.
Yeah, it might be. I mean, also that's maybe not because it's not obvious if you don't actually produce some for whatever reason in a phase transition, just dynamically. But yeah, it's just very difficult to check. Even production of any magnetic fields right now is kind of, I mean, there are simulations of that, but the simulations are done in a regime in which the electroweak phase transition cannot proceed at all.
Yes, right. So
because it's only
long
pure
after that.
vacuum.
Yeah.
So it's tough. I mean, I'm sure there will be some produced, but the estimates we have, it's like 10% of the total energy going to magnetic fields. That's a little bit, let's say, from a simplified analysis. Yeah, well, but that's just because of the, let's say, generic problems with phase transitions, which is that they are difficult to model.
We also mentioned that you could generate primordial magnetic fields through inflation. Are there any other cosmological mechanisms that could produce primordial magnetic fields?
Good question. I don't think that I know any. But
Because
I think mainly it's inflation and phase transition. That's all I know. Yeah.
Interesting. So yeah, okay. So if we can pin down that this magnetic field is of primordial origin, then it's tightly connected to either having a phase transition or inflation. This is exciting. Could you, Helen, please also explain once more why the belief is that this could be this magnetic field could be of primordial origin?
Because it's hard to explain this by the standard picture. So we have some magnetic fields in our galaxies or clusters, but it's hard for them to be extended to the void. So there's nothing there, no interactions. So it could possibly be a primordial thing, so it's everywhere.
I see.
Yeah.
Thank you. I see that we have a question in the chat. The question is, can preheating produce primordial magnetic fields?
I would say yes. That's just a guess, but it can produce. It is not unlike a phase transition. So if you add the appropriate term to the Lagrangian, I'm sure it will.
Yeah, I would say the same. I hope this answered your question, Anish.
Yeah, but in practice, I never tried to do this, so I won't even recall how the term should look like. Sorry.
Yeah, same here. I maybe want to come back to just what you do you think magnetic fields could also play a role in combination with gravitational waves as like a multi-messenger observation? So what I'm thinking about concretely is, for example, you could axions, you could produce photons in a magnetic field. You could try to detect these photons, and at the same time, if you have a cloud of axions around, say, like a massive black hole, you could also detect gravitational waves. So I'm wondering if there are more of these multi-messenger probes that should explore in the future, like combining magnetic fields and gravitational waves or any other probes.
Primordial. Well, but I guess because in galaxies you have quite a lot of magnetic fields just by dynamo generated. So that's if anything is in a galaxy, then it's tough, I would think.
Yeah, I agree with that.
Yeah, although I really don't know to what extent that is a problem. But then again, so I've seen papers talking about how you can have outflow of magnetic fields from galaxies because they were, I think, trying to cover the voids. But again, it wasn't clear to me to what extent that actually works. I mean, what fraction of them can you cover?
Right.
I guess in terms of multi-messenger in general, there's also neutrinos, right? We could look for neutrinos plus photons plus gravitational waves. I guess the prototypical thing here would be a supernovae event, right? Where we could observe all three. Not early universe anymore, but
right. But in terms of looking for physics beyond the standard model, do you have something in mind that could look further? I mean, neutrinos are, yeah, interesting from an astrophysical point of view.
I'm not sure if maybe having all three, the gravitational waves plus the neutrinos and the photons gives you anything new about maybe like the energies involved and how energy is dissipated in a supernovae. And maybe that could be some sort of extra handle on some new physics, like maybe something about the neutrinos. But I'm not sure. I mean, we've already seen multi-messenger events with neutrinos, right? Like supernova 1987A, right?
Right.
So I'm not sure how much the gravitational waves add to that story.
Right. Yeah, so in that perspective, it's maybe difficult to think about that. Then it's again rather combining different observations instead of this multi-messenger story. Yeah. There's one more question in the chat, which is again towards the primordial magnetic fields, I think. The question is, or could the universe start from an anisotropic magnetic field background instead of a homogeneous? From anisotropic magnetic field background.
But I would well, the safest assumption isn't that it's homogeneous, but that it's actually exactly zero, right? So I guess the answer is yes, but anisotropic vector fields. No, but why? Are you talking about, say, initial conditions for inflation? And there are no bounds, but also you don't really want that, do you?
Yeah, no, so I'm for inflation. Okay, why not just maybe make sure the perturbations are stable?
Well, but you want the inflaton to dominate. You don't want anything to spoil that. So it would have to be diluted by inflation, right? That's not. Otherwise, you just produce it at the end.
Yeah.
Although I don't know how it scales, because you can have, I mean, with strings, you can, because they just go as A to -2, so you can dilute them a little bit with inflation, and they will still grow back. So they can grow back, let's say recently. Maybe you can do that with magnetic. No, but magnetic fields go like radiation, right? So then it's that's worse.
Yeah.
What if you don't have inflation? Whoa. That's crazy talk.
Of course, you can go beyond that and you can give up on inflation, but yeah, that's okay. Right. So
the answer is I have no idea with bouncing universes. Maybe you can, but I would expect it to work a little bit like inflation, at least to some extent.
Yeah, I don't know about that. But yeah, I mean, could be interesting to explore, but it's maybe not a standard avenue. Okay. I think I would like to summarize this panel discussion session, because we had a nice transition also back and forth between cosmology and astrophysics. So first of all, I want to thank the panelists again, so Helen, Tessa, and Chris. Thank you very much for sharing your perspective, ideas about future and current research, giving some input. I think we talked a lot about different ideas. We covered the whole gravitational wave spectrum from pulsar timing arrays to these observations to LIGO and beyond. We talked about astrophysical sources, how we can use them to search for physics beyond the standard model, primordial black holes. We also talked about modifications of gravity, dark sirens, how we can learn more about cosmology. So I think this reflects how broad this field is, how many possibilities we have, and how much exciting science we can do in the future. So thanks so much for joining this panel discussion. Thanks so much for all the questions from the audience and to everybody who contributed. And I think I would hand back them to the organizers.
Thank you, Laura.
Yeah, thank you, Laura.
Thank you.
You're welcome.
Okay, so now I think we will have our closing talk by John.
Okay, well, it's not really a talk, and I apologize that I wasn't able to participate in all the panel discussion because I had something else that clashed with it. But anyway, Laura, thanks very much for chairing the discussion. The half of it which I heard was certainly very interesting. So as I commented at the beginning of this workshop, I'm not really an organizer. So Eric and Rishuka, Alish, and I don't see all the other organizers, but anyway, they're the real organizers, not me. Anyway, I think the gravitational waves have clearly opened up totally new horizons in astrophysics. We've been able to see in motion objects that perhaps we didn't even dream existed. And I think there's tremendous scope there within the general domain of astrophysics. But I think that the group represented here, as was just described at the end there, was the primary motivation for being interested in gravitational waves, I think, is to use them as probes of possible physics beyond the standard model. And there's a wide variety of possibilities for that have been discussed during the course of the workshop. And I'm not going to go through them all, but the thing which I find fascinating about this subject is that gravitational waves, in principle, give us a possibility of probing physics at scales many orders of magnitude beyond what we could hope to ever reach with experiments in a laboratory. I mean, nobody will ever build a terrestrial collider to compete with the cosmological collider, for example. We will never observe in the laboratory a phase transition at a temperature of 10 to the 5 GeV. So there's going to be this big sort of gap in our understanding of the way that the universe developed between what the LHC can show us and possibly the next generation collider and what we can infer from cosmology and potentially gravitational waves. So there's a few things that I found particularly interesting today in topics that were discussed. So we heard from Raffaele about these ideas for detecting high-frequency gravitational waves. And clearly those would come directly from some high energy phenomenon in the early universe, presumably. Raffaele didn't have the time to tell us so much about what the possible sources of those high-frequency gravitational waves might be. But this, I think, is a very interesting topic and something which certainly I would like to think more about than I've taken the time to think about so far. I also found what Tessa was saying about testing the propagation of gravitational waves was very interesting. I mean, I thought about things like probing the mass of the graviton and looking for Lorentz violation. But I think that Tessa showed us that, in fact, there's a lot more things that you can do potentially in the future with future generations of gravitational wave detectors, probing Hornetsky theories and the like. So that's also very interesting. So I just hope that with gravitational waves, we will soon, as I said, be able to get out of the phase of discovering new astrophysics and get into the stage of discovering new particle physics, something beyond the standard model. And so I have a few of my favorite topics there. One of them is cosmic strings. So Marek and I have a shared interest in cosmic strings. We have this effect that was first observed by nanograv, seems to be confirmed by other pulsar timing arrays. The astrophysicist is going to tell us, oh, no, Yahoo, that's those supermassive black holes. But I still hope, keeping my fingers crossed, that it's not, supermassive black holes, and might actually be cosmic strings, which would then be observable over a whole range of frequencies, including the frequencies that can be probed using the Nancy Roman laboratory. So I think that's one of my personal favorites for a possible window on high energy particle physics. But as I mentioned, there are many, many others. So anyway, I think that's really all I can think of to say. I think that there's been a lot of exciting topics mentioned at this workshop. In particular, a lot of interesting topics today. And I look forward to the next one in the series, always assuming that Nobuchuka and Anish and Marek and friends can summon up the energy to keep on organizing these workshops, because I think it really fulfills a niche which is not covered by many of the other workshops on gravitational waves. So again, friends, thanks very much for organizing, and thanks to everybody for participating so actively.
Thanks. Yes.
Thank you very much. Oh, we're done.
So it's beer time now.
It is, yes. It seems so.
Okay, so let's keep in touch.
Yeah, keep in touch. Thank you very much.
Thank you.
Once again, see you soon.
Yes,
Thank you
sir.
very much.
Keep in
Bye.
touch. Bye.
Bye. Thank you.
Thanks, Marek.
Thanks.
Oh, I look at the setup. Yeah, I look at the setup and for the next time. Okay. Yeah. Thank you very much. Yeah, keep in touch. And yeah, thank you.
Yeah, that's